We now start chapter 8 module 2, where we continue our discussion on modules. In module 1 we learnt basic definitions and some basic properties. We introduced the notion of submodules, sums, direct sums and quotients, and we saw that it is almost similar to that of vector spaces. Now we will see that there are some differences between module structures and the vector space structures, and the difference comes from the fact that a base ring may have a lot of non-invertible elements, in fact non-zero non-invertible elements. We will introduce the notion of linear independence, basis, and the concept of free modules. And we will also finally list down some basic differences between a module and a vector space. Let us start. Let R be a commutative ring with identity. Let S be a non-empty subset of a module M over R. We say that S is linearly independent over R if for every distinct V1, V2 and so on Vn in S and C1, C2 and so on Cn in R, we have C1 V1 plus C2 V2 and so on Cn Vn is equal to the 0 element of the module implies C1 is equal to C2 and so on Cn is equal to 0 for all I. As usual, the 0 in boldface denotes the additive identity of the module M, and the usual 0 denotes the additive identity of the base string R. A subset S is called linearly dependent if it is not linearly independent over R. So, we see that the definition of linear independence of a set in a module is the same as that for vector spaces. Example, let R be the ring of integers, let M be the ring of integers as well, then obviously M is a Z module. Then the set containing the elements 4 and 5 is linearly dependent because of this relation 5 times 4 minus 4 times 5 is 0. Now look at the ring R, which is the collection of all polynomials over the real field, and that is the module as well M. Here the set singleton 1 is linearly independent over the base ring R, but the set containing 1 and x is linearly dependent over the base ring R. Definition: let M be an R module. A non-zero element M in the module M is called a torsion element of M if C dot M is 0 for some non-zero element C in the ring R, and the collection of all torsion elements of M together with the 0 element of M is called the torsion submodule of M and usually denoted by tor M. A module M is called torsion free if the torsion submodule, that is tor M, is the trivial submodule, that is the singleton 0 vector, and it is called a torsion module if the torsion submodule tor M is the full module M. One more definition: let M be an R module and V an element in M. The annihilator of the element V is defined as an V, which is the collection of all elements C in the base string R such that C dot V is 0. The annihilator of a submodule n is defined as an n, that is the collection of C in R such that C dot V is 0 for all V in the submodule n. It is easy to verify that both an V and an n are ideals in the ring R. Definition: let M be an R module. A subset B of M is called a basis for the module M if it is linearly independent and if span of B is M. An R module M is said to be free if either M is the trivial module, that is the singleton 0, or if M has a basis. We say that M is free on B if the set B is a basis for M. Some examples: every vector space over a field is a free module, because we know that every non-trivial vector space has a basis. Next example, the module Z as a Z module is a free module and it is free on singleton 1. That means singleton 1 is a basis for the Z module Z. Example, the module Zn over Z is a torsion module and therefore it cannot be free, because we cannot have a linearly independent subset, and it is not true therefore that every module is free, unlike vector spaces. Example, the module Z cross Z is free as a Z module. We can characterize a basis for a module in the following theorem analogous to vector spaces, and it can be proved in a similar fashion. So, let B be a basis for a module M over R. Then 1. Every element in M can be expressed as a unique linear combination of elements of B. 2. B is a minimal spanning set. 3. B is a maximal linearly independent set, where maximality and minimality are with respect to set inclusion. We know that every non-trivial vector space has a basis, and it is not true that every non-trivial module has a basis. For example, the module Zn over Z, where every element is a torsion element, and therefore we cannot have a linearly independent set and therefore not a basis. But we can prove that if a module has a basis, then any two bases have the same cardinality, just like vector spaces. What is interesting here is that to prove this statement, we have to take help of a vector space. We will see that by extending the base ring, we can create a vector space which is naturally associated to this module. Then we will use the fact that for a vector space any two bases have the same cardinality, and use that to prove that any two bases in a free module have the same cardinality. Once we prove that, the cardinality of a basis is a well-defined notion, and that is what is called the rank of a free module. Theorem: let M be a free R module, then the following statements are true. 1. Any two bases of M have the same cardinality. 2. The cardinality of a spanning set of M is greater than or equal to that of a basis for M. We do not necessarily mean that these bases are with finitely many elements. So, when we say the same cardinality, we mean that if we took any two bases for M, then there is a bijective map from one to the other. Proof of part 1. We will try to associate a vector space to the module M, and we know that both these facts are true for vector spaces, and that we will be using to prove the statement for modules. Let us choose a maximal ideal M in the ring R, which we know that it exists because R is a commutative ring with identity, and take the quotient ring R modulo M. M being a maximal ideal, the quotient ring is a field denoted by F. Now, we cannot expect to have a natural module structure of M over F. We can have a natural module structure if we take a suitable quotient of M, and that is given by M dash, which is M quotient MM. You can see that MM is the submodule of M, and the elements of the submodule MM look like the linear combinations summation Ci Vi, where Ci's are from the maximal ideal M and the Vi's are from the module M. In this case, the definition C bar dot V bar is equal to C dot V bar for C bar in the field F and V in M is a well defined scalar multiplication on M dash. And it is easy to verify that M dash is a vector space over the field F with respect to this scalar multiplication, and the addition structure comes from the quotient module. Let pi from M to M dash denote the canonical surjection onto M dash defined by pi of V is equal to V bar. You know, V bar is nothing but the equivalence class of V or the coset V plus MM. Let B denote a basis for the module M and B bar denote the set pi of B. We observe that B bar spans M dash for if we take a linear combination C1 V1 etc. up to Ck Vk, which is denoted by V, where C1 C2 Cn are in R and V1 V2 Vn are in B, then V bar is C1 bar dot V1 bar plus dot 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 Cn bar dot Vn bar. Therefore, B bar spans M dash. We now show that B bar is linearly independent over the field F. Let C1 C2 Ck be elements in the base ring R and V1 V2 Vk be in the basis B, such that C1 bar dot V1 bar plus etc. plus Ck bar dot Vk bar is 0 bar. Therefore, C1 dot V1 plus etc. Ck dot Vk belongs to the submodule MM, and therefore we can write this linear combination C1 dot V1 plus etc. plus Ck dot Vk as summation k is equal to 1 to R Cik Vik, where Ciks are elements in the maximal ideal M and Viks are elements in the basis B. By the linear independence of the basis B, we conclude that Ci's are also in M. Therefore, B bar is a basis for the vector space M dash over F. Hence, the cardinality of B bar, which is dimension of M dash over F, is a well defined number. Hence, it follows that any two bases for M have the same cardinality. Proof of part 2. If S is a spanning set for the module M over R, then S bar, which is pi of S, is also a spanning set for the module M dash over F. This we have seen just now when we proved that B bar spans M dash. Hence, it follows that cardinality of S, which is greater than or equal to cardinality of S bar, which is greater than or equal to the dimension of M dash over F, and finally it follows that cardinality of S is greater than or equal to cardinality of B. This completes the proof of the theorem. Now, a remark: we can define modules over non-commutative rings as well, but the theorem proved above is not true if we change the base ring to a non-commutative ring. Definition: let M be a non-zero free R module. The rank of M is the cardinality of a basis for M. This number is denoted by rank M, and the rank of the 0 module is defined to be 0. Now, let us start with a non-empty set B and a commutative ring with identity R. Let R box B denote the set of all functions with finite support on B, that is, set of all f from B to R such that Fb is 0 for all but finitely many B in B. The set R box B has a natural R module structure given by pointwise addition and scalar multiplication. Moreover, R box B is a free R module with a basis given by these functions chi B, where B is running through the set B, and the functions chi B's are defined as chi B of x is equal to 1 if x is equal to B and 0 if x is not equal to B. Then it is easy to check that the set chi B is linearly independent and it spans the module R box B. So, this is a basis and it is called the standard basis for the module R box B over the ring R. Theorem: let M be a free R module with basis B, then M is isomorphic to R box B. To prove isomorphism between M and RB, we have to define a function on the basis B and then extend it by linearity. But we have to check that it is an isomorphism. So, what we do is the following: we define the function phi from M to R box B as phi of B is equal to chi B for B in B and extend it on the whole of M by linearity. Then automatically this defines a homomorphism from M to R box B. This is an isomorphism because it maps a basis to a basis. Recall that chi B is a basis for the module R box B, and therefore phi is an isomorphism. Theorem: let M and M dash be free R modules over R, where R is a commutative ring with identity. Then M is isomorphic to M dash if and only if rank of M is equal to rank of M dash. Proof: if M is isomorphic to M dash, then any isomorphism maps a basis of M to a basis of M dash. It follows from the bijectivity of an isomorphism that rank of M is equal to rank of M dash. Now suppose that rank of M is equal to rank of M dash. Let B and B dash denote basis for M and M dash respectively. We know that rank of M is equal to rank of M dash, and therefore cardinality of B is the same as cardinality of B dash, which means that there is a bijection from B to B dash and call it eta. This bijection can be extended by linearity on the whole of M. So, this eta gives rise to a homomorphism from M to M dash, and this is an isomorphism because it maps a basis to a basis. Theorem: let R be an integral domain and let M be a free R module. Then all the linearly independent sets have cardinality at most rank of M. Proof: let B denote a basis for the free module M over R. We know that M is isomorphic to the module R box B. Therefore, it is enough to prove the result for the free module R box B. Let Q denote the field of fractions of the integral domain R. We know that it exists, and it is clear that R box B is contained in Q box B, because R is contained in Q. Moreover, rank of M, which is the same as rank of R box B, and that is the same as rank of Q box B. Now, let L denote a linearly independent set in M over R. We show that L is also linearly independent over Q as a subset of Q box B. If we can show that, then we are done, because Q box B is a vector space over Q, and we know that this statement is true for vector spaces, and therefore we can use that to show that this statement holds for a free module over an integral domain. Now, to prove that L is linearly independent over Q as a subset of Q box B, let us assume that Ci by Di are elements in Q and Vi are elements in L for I is equal to 1 to n, and suppose that summation I equal to 1 to n Ci by Di dot Vi is 0. So, we have a linear combination of the elements V1, V2, Vn, but over Q, and this expression gives rise to summation I equal to 1 to n dCi by Di times Vi is equal to 0. If we multiply the expression by d, which is the product of d1, d2 and so on up to dn. Hence, Ci is 0 for all I equal to 1 to n, that is from the linear independence of the set L. Therefore, L is linearly independent over Q, and that proves the theorem, since Q box B is a vector space over the field Q. Let us state a theorem which is extremely useful, and the proof is not difficult at all. The theorem says, let M be a module over a ring R which is commutative with identity, then the following statements are true. 1. If F from M to F is a surjective homomorphism of modules where F is a free module, then M is isomorphic to this external direct sum of kernel F and the free module F. Here of course the free module is playing a big role, otherwise we cannot have this external direct sum. Then the part 2 says if n is a submodule of M and if M and M quotient n are free, then M is isomorphic to the external direct sum of n and M quotient n. Well, this is a spatial situation which follows from 1, you can see, because we will take the canonical surjection in this case, the map pi from M to M quotient n, and if we assume that M quotient n is free and also M is free, then we can apply 1 and then the result would follow. Note that the kernel of the canonical surjection is n. Moreover, if M, n and M quotient n are all free, then rank of M is equal to rank of n plus rank of M quotient n, and if all the ranks are finite, then rank of M quotient n is rank of M minus rank of n. We have already seen this result for vector spaces, where we stated this in terms of dimension, which is of course the rank for modules, and we see that if we have a free module of finite rank such that all of them M, n and M quotient n are free with finite rank, then we have a similar formula involving ranks. Example, take M to be the Z module Z and n the submodule nz for some positive integer n. Then the quotient module M quotient n, which is Z quotient nz, is in fact isomorphic to the module Zn. The module M is of course a free Z module, but not the quotient, because we know that the module Zn has only torsion elements and therefore it cannot be free. Let us now list down some basic differences between vector spaces and modules. 1. A submodule n of a module M need not have a complement, that is, there may not exist a submodule T such that M is equal to the internal direct sum n direct sum T. 2. A submodule of a finitely generated module need not be finitely generated, we have seen an example. 3. There exist modules which are not free. Of course, there are the torsion modules like Zn which cannot be free. And 4. A minimal spanning set or a maximal linearly independent set is not necessarily a basis. So, these are some major differences between vector space structure and module structure, and that happens because of existence of non-zero, non-invertible elements in a ring. We have seen a lot of similarity in vector space and module structures, but there are some important differences and we have more or less summarized them. But what is important is that if we have a vector space over a field F and a linear operator T, then the vector space has a natural module structure over the polynomial ring Fx through the linear operator T, and that is extremely useful, especially in the structure of canonical forms of the operator T.